If you look up on a cold winter night, you might spot the 3 stars of Orion's belt. Just a smudge below them is the Orion Nebula. It's a place where the universe is still making its first drafts. To understand what we're looking for out there, we have to start with the basic rules of how matter sorts itself out. The first rule goes like this. If a massive cloud of gas and dust collapses under its own gravity, it spins up and heats until the hydrogen ignites, and you get a star. If only a little mass piles up, specifically anything below 13 times the weight of Jupiter, fusion can't even sputter. You get a planet. And planets are supposed to form safely inside the leftover disks of gas and dust orbiting around a young star. For a long time, humanity's understanding of the cosmos has relied on these strict categories. You have stars and you have planets. Every object has a predictable origin, a defined label, and a specific place it belongs. In October 2023, 2 astronomers pointed the most powerful piece of hardware ever built at our local sky. They were looking for a clean census of baby stars and small brown dwarfs. Their target was the Trapezium Cluster, a million-year-old stellar nursery locked tight inside the center of the Orion Nebula. They found 540 free-floating planetary-mass objects, but buried in that data was a detail that broke the models. 40 of them came in pairs, 2 isolated worlds drifting together in the dark, with absolutely no host star in sight. This is a visual scale showing the distance between the Earth and the Sun, what we call 1 astronomical unit. These paired worlds are separated by 384 astronomical units, 10 times farther apart than Pluto from our Sun. In the dark, they hold on to each other, orbiting a shared center of gravity with 0 mass in the middle. These are the Jupiter mass binary objects, or jumbos, and they shouldn't exist. Stars do not form this small, and if a massive planet gets violently ejected from its solar system, it doesn't bring a friend. 40 pairs out of this population is near 10%. It is not a statistical fluke. When a discovery threatens a foundational rule of physics, the first step is to check the data. In 2024, astronomer Kevin Luhman ran a counter-analysis that offered a much safer explanation. The Orion Nebula is incredibly dusty. If you have an old star sitting far behind the nebula, its light travels through that dust. The dust scatters the shorter blue wavelengths, leaving only a reddened beam by the time it hits the telescope. This chart shows how astronomers plot the color of incoming light to separate young brown dwarfs from background contamination. That scattered red light lands in the same neighborhood as cool planetary-mass objects. The telescope sees a planet, but the reality is an optical illusion. Luhman pulled the follow-up spectra. For many of the objects, including a highly studied pair called Jumbo 24, the light signature was actually an M-class red dwarf star sitting miles behind the nebula. Under this lens, the Jumbo paradox deflates. The bizarre planetary pairs appear to be a mirage of background stars, and the laws of planetary formation hold up. But the universe rarely cooperates with a clean wrap-up. While Luhman was looking in optical and infrared, another team decided to listen. They turned a sprawling array of radio dishes in New Mexico toward the exact same coordinates. Of all the pairs they scanned, only one rang back. It was Jumbo 24, the exact same system that Luhman had just argued was a background star, and it was emitting a remarkably strong radio signal. Stars and larger brown dwarfs produce radio waves by heating tangled plasma with their intense magnetic fields. But that mechanism does not scale down to something the size of Jupiter. Free-floating planets lack the internal mechanics to produce radio waves this strong. We are left with a massive contradiction. If Jumbo 24 is a background star, it explains the radio signal, but the optical data is completely wrong. If it's a binary planet, the optical data is right, but the radio emissions defy the laws of physics. The object changes entirely depending on which instrument you use to measure it. Faced with a breakdown in the data, theorists have been working to build a model that allows these things to exist without breaking the rest of physics. In February of 2025, a new mechanism emerged. Researchers ran advanced hydrodynamic simulations. They mapped exactly what happens when two young stars wander past each other in a dense cluster. At closest approach, their surrounding disks of gas and dust don't quite collide, but the immense gravity tugs on them. A tidal bridge of compressed gas stretches across the gap between the stars, and then it violently fragments. The simulation shows that up to 14% of those dense clumps break off as paired Jupiter-mass binaries. It is a violent, believable process that produces exactly the kind of population we see in the trapezium. But even this model fails to explain the radio emissions. Our ability to gather data has simply outpaced our theories to explain it. As of today, the formal status of the jumbos in the astronomical community is that whether they even exist remains an unsolved problem. The friction here comes from how we built our taxonomy. We defined what a star is based on our sun, and what a planet is based on Jupiter. We built our scientific rules from the bright, easy cases right in our own neighborhood. But the Orion Nebula is a chaotic, million-year-old rough draft. It is an environment where the matter between stars is still violently sorting itself out, and the clean boundaries we drew simply haven't settled yet. We draw lines for our own convenience, but the cosmos does not owe humanity tidy boxes. Every time we build a sharper lens and point it into the dark, the rigid categories we rely on begin to fail. If you enjoy following the evidence into the places where the textbooks break down, consider subscribing. We spend a lot of time out here looking at the unresolved edges of science. Let me know in the comments, which tidy box of physics do you think the next generation of telescopes will dismantle? Until then, keep looking up. The sky is still full of things we haven't named.